Okay, today I'd like to share a way to do dynamic modeling of non-Poisson neurons. Basically, we usually use the Poisson model to describe neural activities. But when we evaluate the final factor, that is variance to mean ratio, we'll see the Poisson assumption is quite unrealistic. Well, if neurons are Poisson, then the final factor will lie roughly around 1. But based on this plot, you can see the real neurons are far from Poisson. It can be over and under dispersed. Moreover, the neural activities will naturally change along the time. So neurons can be both non-Poisson and non-stationary. And the goal for this research is to handle these two simultaneously. Well, first to handle the non-Poisson neurons, that is to describe the over and under dispersed neural spikes, we use the Conway-Maxwell Poisson distribution, that is the CMP. CMP distribution is a general extension of the Poisson distribution, which has two parameters, and the dispersion parameter nu just controls different pattern of the dispersion. Okay, now we have the observation model, but how to track the change of the neural spikes? Here we choose to use a state space model to capture dynamics of two parameters in CMP. Basically, we model those two parameters by two-log linear model like this. And those state space parameters or latent vectors at step k are summarized as theta k. At each step, before seeing the data, we assume the state vectors progress linearly with the Gaussian noise. Then, if we plug in the likelihood, we'll get the posterior update. But since the likelihood is CMP distributed, there's no closed posterior. Here we choose to use the normal approximation to approximate the posterior. One fast way to do that is to evaluate things at recursive prior. And this is a general form for the algorithm. This is great because it's just one-time calculation, but there are some problems. First, the hashing is not robust to outliers, and secondly, the estimated posterior might bias too much if true values are far from recursive prior, and this problem is even be exacerbated for a dynamic CMP model. So there are some improvements. We can routinely use the RTS smoother to improve the filtering estimate. And first, to ensure the robustness, we just replace the observed information with the expected information. And secondly, to reduce bias or make use of data more efficiently, we do the exact Laplace approximation and the posterior mode, that is the MAP. Okay, then we apply our method to two real data sets. In the first application, we use the hippocampus data. Basically, in this experiment, we let a rat run back and forth along linear track like this. And this is a record from one neuron in hippocampus area. The black dot just corresponds to neural spikes. We can observe that there's a place field where neuron fires at specific locations, and these locations tend to change over time. The following two panels show the fitted results. In the first panel, according to the fitted mean firing rate, we successfully recover the changing location of the place field, like this. Moreover, when looking at the fitted final factor, we show that the spiking within the place field is over dispersed. And the final factor also changes along the time. Then in the second application, we fit the neural activities from V1 area. In this experiment, we let the monkey to see a sequence of movies with 100 different grading orientations. The trials are repeated 120 times. This is a neuron from one neural activity from one neuron. Here I show the average tuning curves in different epochs of the trial. Generally speaking, there are two peaks in the tuning curve, a smaller one and a larger one. But as trial going on, the overall firing rate goes up. And these two plots just show detailed change across trials in two specific locations or direction. In terms of the mean and the final factor, basically the mean firing rate goes up and the final factor goes down. Using subset of the data as training, we fit the model and can successfully recover the observed pattern in detail. But this is just one neuron. We further fit several different models for 74 neurons and compare their performance in terms of log2 likelihoods per spike in training and test data set. Basically, you can see using the Poisson model, no matter it's static or dynamic, the performance is worse than the others. That means considering the dispersion is very important, moreover, using the dynamic CMP allows us to extract more information from neural activities, especially in terms of the dispersion pattern. Okay, that's all. Thank you so much.